Our next one is 1 petal of r equals 4 sine of 3 theta. Well, since it's telling you that you want to do 1 petal, you already know that you're a rose. So I'm already told that this is a rose. Now for roses and lemniscates, what we do to find our limits of integration is we use tangents at the pole. So let's go ahead and find the tangents at the pole first. Recall to find the tangents at the pole, you let r equal 0 and solve for theta. We don't have to check to make sure that r prime doesn't equal 0 for these because they are tangents at the pole. So here if I'm solving where r equals 0, first I divide by 4, and then I have to figure out where does the sine equal 0. Remember, bring down your 3 theta. I'm going to have 3 tangents at the pole because the number multiplying theta is equal to 3. So where does the sine equal 0? The first 3 values. Well, at 0, and then at pi, and then at 2 pi. Solving for theta by dividing everything by 3, we'd have theta is equal to 0, pi over 3, and 2 pi over 3. So these are my tangents at the pole. Let me go ahead and show you how to graph this. So I know it's a rose. My n is equal to 3, so I know I'm going to have 3 petals. I also know it's sine, therefore my first petal is going to be at 90 degrees divided by n, so at 30 degrees. And then in radians, I know that's pi over 6. And then my next petal is at 360 degrees divided by the number of petals, which is 3, or 120 degrees. So I know 30 plus 120 is going to put me at 150 degrees, which is 5 pi over 6. So just to draw all this in, making it a little easier for us. So first draw in those tangents at the pole. I'm going to draw them in kind of like asymptotes because they're not really part of the graph. So here's the tangent at the pole for theta equals 0. Here's the tangent at the pole for theta equals pi over 3. And here's the tangent at the pole for theta equals 2 pi over 3. Now I know that my first petal is at pi over 6 or 30 degrees. That's going to be right here. And my next petal is at 5 pi over 6. That's going to be over here. I know I have 3 petals. So notice that here I'd have 1 petal, and then the next petal lies between these 2 tangents at the pole. So if I go back and I erase this, notice that I put in my tangent at the pole and then I would be split up into 1, 2, 3, 4, 5, 6 sections. If you have an odd number of petals, then you're going to skip a section for each petal. So your first petal is going to be between the first 2 tangents at the pole, skip the next section. Your next petal is between the next 2 tangents at the pole, skip the next section. And then your next petal is between those 2 tangents at the pole, skip the last section. But we can also again figure that out because we knew that our first petal was at 30 degrees, our next petal would be at 150 degrees, and our other petal would be at 270 degrees. So we could figure it out more than one way there, but the tangents at the pole will help us determine what angles our petals lie between. Now again, why do I want those tangents at the pole? Because I only want 1 petal, so I want the interior of just one of these guys. Well, I need the limits of integration for that. Well, the tangents at the pole will tell us the limits of integration. It's going to be between 0 and pi over 3 because that's where 1 petal was graphed. So between 0 and pi over 3. Therefore, we know here that our area is going to equal 1/2 times the integral from 0 to pi over 3 of r, which is 4 sine of 3 theta squared d theta. And again, it's from 0 to pi over 3 because I want 1 petal, and those tangents at the pole are going to tell us where our petals are trapped between. Now if I square that, I end up with 16 sine squared of 3 theta. I can pull that 16 out because it's a constant multiplier. But I have sine squared, so I know I'm going to have to use a power reduction formula. So with that power reduction formula for sine, I know it's going to be 1 minus the cosine of twice that angle, which is 6 theta in this case. And then don't forget to multiply it by a half. Moving over here, so I have 16 over 2, which is 8, times a half, and that's just going to clean up to 4. So I have 4 times the integral from 0 to pi over 3 of 1 minus the cosine of 6 theta d theta. Well, I'm basic form. I can integrate every single one of these. So if I integrate 1, I end up with theta. Here the coefficient of theta is 6, so I know I'm multiplying by 1/6, and the integral of the cosine of 6 theta is the sine of 6 theta. And that gets evaluated from 0 to pi over 3. Plugging in the limits of integration, I'd have pi over 3 minus 1 over 6 times the sine of 6 times pi over 3 is 2 pi. Then plugging in the 0, I'd have 0 minus 1/6 times the sine of 0. Well, I know that the sine of 0 is 0, and that the sine of 2 pi is 0. Therefore, my area of one petal here would be 4 pi over 3. Number 4 wants the interior of r squared equals 6 sine of 2 theta. Well, this guy here is a lemniscate. Anytime you have that r squared equal to a number times the sine of 2 theta or a number times the cosine of 2 theta, you're a lemniscate. And a lemniscate just looks like a figure 8. Since it's sine, I know it's going to have symmetry to the line theta equals pi over 4. To find the limits of integration for a lemniscate, you're going to also use the tangents at the pole. So set the function equal to 0 and solve for theta. Well, the number multiplying theta is 2, so I know I'm going to have 2 tangents at the pole. Start by dividing by 6. Then, where is the sine equal to 0? The first two answers, 0 and pi. Divide by 2 to solve for theta, and theta is equal to 0 and pi over 2. If we draw that, here's theta equals 0. Here's theta equal pi over 2. I know that I have symmetry with respect to the line theta equals pi over 4. So my lemniscate will look like this. And I want the interior of this lemniscate. We are going to use symmetry to find our limits of integration. Therefore, the limits of integration that we are going to use are from 0 to pi over 2, that graphs half of it. So we're going to take those limits of integration and multiply it by 2 to find the area of this lemniscate. So our area here is going to equal 2 times a half the integral from 0 to pi over 2, because again, between 0 and pi over 2, we drew half of our lemniscate. And then be careful here. Remember, the area formula is 1/2 times the integral from alpha to beta of r squared d theta. Notice that this is r squared. It's given as r squared, so you won't be squaring 6 sine of 2 theta because it's already squared. These will cancel here, and then we're in basic form, so we can go ahead and integrate. 6 is a constant multiplier, it multiplies along. The coefficient of theta is equal to 2, so I know I'm going to multiply by a half. And then the integral of the sine of 2 theta is going to be negative cosine of 2 theta. And that gets evaluated from 0 to pi over 2. Cleaning that up, that's going to be negative 3 cosine of 2 theta, evaluated from 0 to pi over 2. Now plugging in those limits of integration, I have negative 3 cosine. If I plug in a pi over 2, that's pi. And then minus the negative is plus 3, and then the cosine of 0. Well, the cosine of pi is negative 1. So here we have negative 3 times negative 1, or 3, plus the cosine of 0 is 1. So that's 3. Therefore, my area of the interior of that lemniscate is 6 units squared.